Today we're going to talk about solutions and properties of solutions and also how to do dilution problems. Well, first of all, what is a solution? It's referred to as a homogeneous mixture. I think you remember homogeneous means everything is mixed evenly. So if you look at water molecules, if you have a sodium chloride solution, water molecules and sodium chloride would be evenly mixed. Now when we say sodium chloride, those separate into ions. There we have sodium ions, and there we have chloride ions that are separated. So it's a homogeneous mixture and two or more substances that are in a single phase. So even though the sodium chloride started off as solid, both of them are in the liquid phase. And also they are even throughout. So if you were to take a sample of a homogeneous mixture from any other part, it'd be the same anywhere. So a couple of things about homogeneous mixtures: the particles of one substance randomly mixed with particles of another. And the solvent is the dissolving medium, is a thing that's in a larger amount. Of course, the solute is the thing being dissolved. And when one thing dissolves in another, we say it's soluble, or another word is miscible. So, for example, if you put salt in an aquarium and it dissolves, that would be a solution. So, for example, sodium plus water, sodium chloride plus water will give you a solution. Now notice these ions here are evenly mixed in the solution. So a couple things about this. The solute is usually less than the solvent. Dissolving solute particles cannot be seen. We put them in the drawing just for purposes of representation of what goes on there, but we actually can't see them. They stay mixed in the solvent forever, so as long as the same conditions exist. The next thing, the solute particles are extremely small. They're from 0.01 to 1 nanometer in diameter, so that's super small. So there's lots of types of solutions. You could have a gas in a gas, like our air is a solution. You could have water vapor in air, that's a solution. Now notice when we talk about this, the solute is always in the state of the solvent. So for example, when you have a gas in liquid solution, the gas, which is carbon dioxide, is going to be in the state of the solvent, which is a liquid. So if you have carbonated water, that would be an example of a gaseous solution where you dissolve a gas in solvent. Liquid would be alcohol and water. And so those are various examples, all those listed in your book. And we talked about solid-solid aerostate when we talked about alloys. So how does this work? Well, one thing we find when things dissolve is like dissolves like. So for example, we think of water as being polar. Now even though we look down, these are water molecules right there. We see on water we don't have a negative or positive, but you remember that water is partially positive and partially negative from our discussion on bonding. So we could actually say there's a partial positive on each of the hydrogens. So there's a partial positive there. And there's a partial negative around the oxygen. So what that means is for an ionic substance that has a positive and a negative ion, a cation and an anion, water actually is very effective at dissolving that. For example, the anion here, you see what's happened. All the positive hydrogens are lined up against that. So we see the hydrogens lined up against that. Whereas a cation, which would for example be sodium, all the oxygen atoms are lined up against that. So water is polar, and it dissolves things that are polar. Now we think of ionic things as not being polar, but they have a negative in and a positive in. So that way we say like dissolves like. So when you dissolve an ionic compound in water, polarity plays a big role in that. So the charged ends of water molecules attract the ions, and so they surround them and separate them from the other ions. So it's like one little ion in the ionic crystal is surrounded by a lot of water molecules. And so when you picture this, you want to see, like for example, the sodium is surrounded by the partial negatives of the oxygen, and the chlorine is surrounded by the partial positives of the hydrogen. So, for example, something else that is very soluble and very miscible together is ethanol and water. Now, ethanol, if you think of carbon-hydrogen bonds, they're basically nonpolar. But a significant portion of ethanol, which is the OH, which we see right here, this is not a hydroxide, it's actually an alcohol group. That's very polar. So that is able to interact with the water molecule, and hopefully you can recognize the type of bond you have here. It's from the OH of the ethanol and the oxygen of the water. This is a hydrogen bond, and this is a very strong intermolecular force, and so that dissolves very well. So another substance we know dissolves in water is sucrose. Now, if we look at the formula, we wouldn't think sucrose would dissolve in water because it's not ionic. We don't see charges. But if you look at a drawing of sucrose molecule, sucrose is C12H22O11. On it, there's a lot of OH groups. So look at all the different OH groups. We see one here. We see one here. We see one here. Each one of these are polar and is attracted to the polar ends of water. And so for that reason, sucrose, or this is table sugar, is readily soluble in water because of the polar ends that exist in a sucrose molecule. Keeps going. Now, like dissolves like, that also means things don't dissolve always well in other things. For example, we see the molecule listed here, this would be considered a nonpolar molecule because this molecule is basically CH3, CH2, and it's nonpolar. There's not a polar into it because carbon-hydrogen bonds are essentially nonpolar. So if we put something like oil and water, those are immiscible. They don't mix because we have a polar solvent, water, and a nonpolar solute, which is the oil. So that doesn't work very well. And the last type of thing we want to look at today is how we do dilution problems. So the definition of a dilution is just adding a solvent to a solution to change the concentration. Now, often we'll start with a solution that's of a known concentration, and that's called a standard. So a standard is a solution whose concentration is accurately known. Now, to do these dilution calculations, we're going to use this formula right here. This is a formula, M1V1 equals M2V2. Now, what do each of these mean? Well, first we see M1. That means the initial molarity. And then we see V1, that means the initial volume. And then on the other side we have M2 and V2. M2 is the second molarity, and V2 is the second volume. Now, one thing about this formula, molarity is always going to be moles per liters, but volume for this, you could use any kind of unit you want to. You just need to be consistent on both sides of the problem. So let's do one of these problems. So a dilution problem, here we go. How much water must be added to 500 milliliters of 0.2 molar hydrochloric acid produce a 0.15 molar solution? So we're going to use a formula we just mentioned, M1V1 equals M2V2. So first you want to look at the initial molarity and the initial volume. So if you read the problem closely, we'll see initially we have this molarity. So our first molarity is 0.2, and we actually initially have 500 milliliters. So that would be our M1 and our V1. And finally, we're trying to get to a 0.15 molar solution, so this will be our M2, our second molarity. So we insert those values in, so we say 500 milliliters times 0.2 molar is equal to V2, that's what we're trying to find, times 0.150 molar. And after you do the math for that, you'll find that V2 is equal to 667 milliliters. Now, that's not actually our answer because that's our final volume. We have to read each of these questions closely. Just looking at the formula doesn't always answer the complete question. It said how much water must be added. Now, V2 is our final volume, so what we need to do here is actually V2 is our final volume, so what we need to do here is subtract the initial volume we started with. So if we say the 667 milliliters, if we say 667 milliliters that we calculated, minus the 500 milliliters that we had initially, we'll end up with 167 milliliters of water, and that's how much must be added. So we have our final answer would be 167 milliliters of water.